Hi guys, we're going to focus on potential energy. So in our first videos, we talked about the work kinetic energy theorem. We focused on just what kinetic energy was. So remember that kinetic energy is 1/2 mv squared. We know that work, if it's constant, is just equal to force times that displacement. And again, that's going to be, if that force is at an angle, it's going to be the cosine theta. So it'd be force cosine theta displacement. If force is varying, then we're going to have to do some kind of integration. So I may give you a function. You may have to integrate that function, and then we'll plug in values based on probably some displacement. Potential energy is also going to be measured in joules. We know that work and kinetic energy are measured in joules. Potential energy will also be the same. So kinetic energy is the amount of energy of motion, and that's really just the energy that's happening in some amount of speed. Remember, it'll be speed and not velocity since these things are scalar quantities. Potential energy is going to be determined by really just the configuration that's within a system. So we have thought about it always as that stored energy, but we like to think about how the forces are interacting internally. So what the forces are doing internally to the system. So it can be specified based on very specific forces acting within a system. So ultimately just stored energy again. If I want to talk about the formula for potential energy, I can think about it in terms of work again. So I can associate work with kinetic energy, and I can associate work with potential energy. So let's say, for example, I have my physics book right here that is at some initial position. We'll call that y sub I. And then I move that physics book up to y sub f, to a final position. It's done some amount of work because I've moved that physics book up in its displacement. It's moved a displacement. So to find the potential energy, I want to think about it by finding work. So if I found the work done by this physics book, then I would think about that applied force. Let's say that we're moving it with a constant, with a constant speed. So if it was at a constant speed, these two forces are going to be equal to one another. So the applied force is just going to be equal to the weight force. So here where I have work is equal to force times displacement, force here is just going to be equal to mg, because I'm going to assume, I'm telling you, it's going to be with a constant force, it's going to be with a constant speed, so these two will be equal. So applied force is just equal to mg, and then delta r is just displacement. So how am I moving that displacement? It started off initially at y sub I, it ends at y sub f. So its displacement would be final minus initial. So y sub f minus y sub I. So ultimately, to find change in potential energy, or to find the work, I'm going to do mgy final minus mgy initial. Okay? So this is just a really simple system for a work being done to find potential energy. Okay? So if I'm thinking about the potential energy for this book, potential energy has to occur over some specific height or over some distance. So I have to be moving up a height to have potential energy. As we lift the book, we can release it and it can fall back to its original position. So it could fall back here, or it could fall back all the way down here to the ground. By lifting it up, it's increased in its amount of potential energy. And it's done that because it's at its highest point, it now has additional room to fall down and have an increase in its velocity, meaning that it's going to have an increase in its kinetic energy. So however much potential energy a system has is going to be equivalent to the kinetic energy that it has. As one rises, the other one falls. So those two have that type of relationship. So we're going to say that potential energy, and specifically this is gravitational potential energy. There's going to be a couple other potential energies that we'll focus on later. So for gravitational potential energy, we're going to say that we find that or symbolize that as U. So we're always going to symbolize potential energy with a U. And we're going to specify specifically gravitational potential energy with a subscript G. So U sub G is going to be equal to mgy, or mass times acceleration due to gravity times whatever height value that is. Its units are joules, and it is a scalar quantity. I may also be able to find the work done by the change in gravitational potential energy of a system. So there's not anything that's called the work gravitational potential energy theorem, but it works just the same. So I could find work based on the change in gravitational potential energy, okay? And it always has to be associated with a system of two or more interacting objects. Okay, so for example, let's do a kind of an estimation problem. So I like this one in that it doesn't give you numbers, but they just want you to kind of use logic about it. So it says that a trophy being shown off by a careless athlete slips from the athlete's hands and drops on his foot. Choosing floor level as the y equals 0 point of your coordinate system, estimate the change in gravitational potential energy of the trophy Earth system as the trophy falls. They've given me no numbers, but they're asking me to estimate what this gravitational potential energy could be. Okay, so let's set this up. So they're wanting me to, I am holding a trophy, it slips out of my hands, drops on my foot. And now I'm saying floor is going to be where y equals 0. Here's my trophy. The floor is where y is going to be equal to 0. Okay? This is going to be the athlete. Here's my little trophy. I know that to find potential energy, or that change in potential energy, we're going to call that delta U, and we're going to specifically call it U sub G, because this is going to be gravitational potential energy. And it's gravitational because this is going to drop down, and it's really going to be the weight force and that force of gravity that's interacting with this object, and that's what's causing it to fall. So gravitational potential energy is going to be equal to mgy final minus mgy initial. Well, the object, the system, is the trophy. Okay? So if I'm thinking about the mass of a person is going to be somewhere between like 40 to 70 kilograms, probably if we're thinking about us. So 40 to 70 kilograms. So I want to think or estimate the mass of a trophy. If we're 40 to 70 kilograms, then the mass of the trophy has to be like in the single digits, probably like less than 5, probably like less than 3. How about we choose 2? Does it really matter what you choose? No, but it should be somewhat logical. So if you're somewhere between like 1 and 5 kilograms, I think you're good. So the mass of the trophy, we're going to call that 2 kilograms. Okay, we already know G. We know that G is just 9.8. Okay, but I need to figure out or estimate a y final and a y initial. Well, I know that the floor is at y equals 0, and the trophy is going to come and hit my foot. So it's going to travel this distance y, which that change in y is really just y final minus y initial. Okay, so if I'm thinking about maybe the average height of a person, it's probably just a little bit less than 2 meters. So then if I'm thinking about, I'm holding a trophy then, maybe kind of like right here, then probably the distance from my hand to where my foot is, or the distance from my hand to the floor, maybe like 1.5, 1.4 meters. So let's say that initially, if my floor is 0, let's say initially that trophy is at 1.4 meters. Okay, so that's just kind of a logical number for us to be at. But then it hits my foot. So it's not hitting the floor, which is at y equals 0. Instead, it's hitting my foot. So my foot is probably, I mean, it's not very far off the ground in terms of meters. So maybe that's like 0.05 meters. And again, all of these are just estimates. So I could be kind of close to any of this and it would be okay. Okay, so let's plug all of this in. And then let's see what we would get for a potential energy here for our change in gravitational potential energy. So it's going to be equal to 2 kilograms times 9.8 meters per second squared times y final, which we said we were estimating 0.05 meters. I'm going to take all of that, multiply it, and subtract it from 2 kilograms. So again, I'm going to subtract it from 2 kilograms times 9.8 meters per second squared times my initial, which is 1.4 meters. Okay, if I do that, I should get delta U to be equal to a negative, should be negative 26.4. And that would be joules, since we're talking about potential energy. Okay, but if I think about why it would be a negative, because if I am dropping the trophy, it's losing potential energy because that means it's being converted into kinetic energy. So that potential energy number is going to go down since it's changing into kinetic energy. So this being negative makes sense because all of that potential energy is now being transferred or converted into kinetic. So it makes sense that this would be negative since it's just being dropped and going down toward that y equals 0. So you have another video that's going to be here on your blog, and it's going to continue to talk about different types of potential energies.